It's been now almost a full week that we've been out, and just want to create a quick video here to keep things moving along. Last time we had class, we were talking about magnetic fields. We're talking about how we can visualize these magnetic fields with things like iron filings, and these invisible forces affect different things. One of the things that we wanted to talk about here are what happens when you have a charge that moves through a magnetic field. And this is what's called the magnetic force law. And so last time we had class, we talked really briefly about the right-hand rule. The right-hand rule relates the moving charge through a magnetic field and the force that is felt on that charge. So if we have a particle that's moving through a field, a particle that's moving with a velocity v, it feels a force on from the magnetic field. And we use what's called the right-hand rule. And the right-hand rule, just as a quick review, we take our index finger and that points in the direction of the velocity, or the direction the charge is moving. The middle finger, or coming out of the palm, is pointed in the direction of the magnetic field. So index finger is the velocity, middle finger, or the palm, points in the magnetic field, and the thumb points upwards, or I guess perpendicular to those two vectors in the direction of the forces felt. So because we're now thinking in 3 dimensions, and it's a little harder to think in 3 dimensions on paper, we're going to use this following notation here. We're going to use arrows to indicate up, down, left, right, and then to show that a field is either going into the page or out of the page, we're going to use the following signs. An X indicates it goes into the page, and a dot indicates it comes out of the page. And we use this formula here, relates the force on things. It's called qv cross b. Or more generically, we just say it's the charge measured in coulombs times the velocity multiplied by the magnetic field will give us the force. Before we jump into this problem here, I want to just quickly, we're going to go and look at the right-hand rule problems that we did last time. So these were some of the problems. We did a few of these in class. But let's take a look at this next row of problems here and see how we can use the right-hand rule for these. So in this problem, it says I, which is the current, is coming out of the paper. So that's coming out of the paper like this. And the magnetic field is going to the right. So now I'm going to use my index finger. I'm going to point right on my right hand. And my middle finger is going to point in the direction of the magnetic field, which is going to the right. That's this one right here. And then my thumb points in the upward direction. So for this one, we have a force that is up. The next one, we have a particle, a charged particle moving up. Now the charged particle is moving up, and the magnetic field, I'm rotating my right hand so that the magnetic field, my middle finger, is pointing to the right, and my thumb, you can't see it there, but is now pointing into the page. So here, force is, and I'm going to put an X to show that it's into the page. There's a few of these trickier ones. This one, the current is going up and to the right, and the magnetic field goes into the paper. So again, index finger going this direction. The middle finger points down into the page because it's going into the paper. And my thumb now points 90 degrees off to the left. So this wire is going to feel a force going this way. And then this last one here, we have a current going from right to left. The dots, remember, the dots mean that the field is coming out of the paper. So this, my right hand points to the left. My middle finger points out of the paper, and now my thumb is pointing up. So this wire will feel a force going up. And then let's do one last row here, just as an example. So this one here, we have the current is going to the right, and the force is now going down. So we have to figure out where the magnetic field is. So I'm going to point my index finger to the right, and remember the thumb points in the direction of the force. So the thumb goes down. This goes this way. My index finger points to the right. And it's a little awkward to do this, but if I do this correctly, my middle finger points up and out of the paper. And so I'm going to put dots here. That's the B field out of the page. This one we have the forces going to the right, and the magnetic field, the X's, remember, means goes into the page. So my thumb has to be pointed to the right. And my middle finger has to be pointed into the paper. So into the paper. And this goes, this goes into the paper. And I have to rotate. I'm actually just going to rotate the paper because it's easier, right? So thumb points in the direction of the force. My middle finger points into the paper, and my index finger is pointed down, which is now up because I flipped the paper. So the current, I, goes down. In this problem, it doesn't show the magnetic field, but we define the magnetic field as being from north to south. That's B. And the X indicates that the current is going into the paper. And so index finger points into the paper like this. The magnetic field, my middle finger, goes to the right this way, and my thumb, you can't see, is now pointed down. We'll do this last one here. Here it says the force is an X, which means that it's going into the paper. And the current goes to the right. So I have the thumb and I have the current. I'm trying to figure out the magnetic field. So I have my index finger that's going to point to the right. I have my thumb is going into the page this way. And my last finger, my middle finger, is going down. So I know that in order for this to be felt, there must be a magnetic field down. Hopefully that's a little helpful. Go ahead and check your answers on these. Make sure that you are taking a picture of this and uploading it to Classroom for a grade. Alright, so using all of this, let's take a look at the equations and how this relates to some problems here. So, here's a problem that you will encounter. In fact, in the next homework set, we have a few problems like this. In this problem, it says, a proton enters a magnetic field B, which is directed into the page. Those are shown by the X's on the screen. The proton has a charge plus q and a velocity v, and is moving to the right, and enters the magnetic field perpendicularly. So one of the things that it's given here, the charge on a proton or an electron is equal to 1.6 times 10 to the negative 19th coulombs. here it gives us a velocity, says that it's moving at 4 times 10 to the 6th meters per second, and encounters a magnetic field, B, equal to 0.5 Teslas, and asks us to determine the magnitude and direction of the force. So let's figure out how I'm going to do this. Let's see. All right, so get a clean sheet of paper here. So F is equal to qvB. In the problem, it tells us that the Q is equal to 1.6 times 10 to the negative 19th coulombs. The velocity of this moving proton is equal to, make sure that I have that, it's equal to 4 times 10 to the 6th meters per second. And it encounters a magnetic field equal to 0.5 Teslas. So there's the setup of the problem. And we say F is equal to qvB, 1.6 times 10 to the negative 19th coulombs, times the velocity, 4 times 10 to the 6th meters per second, times 0.5 Teslas. And we plug this into our calculator. Now if you're using your cell phone, cell phones aren't the greatest for doing scientific notation. Hopefully you have a good scientific calculator around. Here, 1.6 E19 negative times 4E6 times 0.5 gives me 3.2 times 10 to the negative 13th. And the units for force are in newtons. All right. So let's take a look at some of the problems that you guys are going to encounter in your homework set. So, number 1 is almost identical to the same problem we just did, but let's do it again here. So, here it says a proton speeding through a synchrotron at 3 times 10 to the 7th meters per second east experiences a magnetic field of 4 Teslas into the page. That is produced by steering magnets inside the synchrotron. What is the magnitude and direction of the magnetic force pulling on the proton? Alright, so, and it gives a hint that says the charge of any proton or electron is this number right here. Okay? Alright, so we have here, we know that F is equal to qvB. We know that the charge, Q, is equal to 1.6 times 10 to the negative 19th coulombs. The velocity on the proton is 3 times 10 to the 7th meters per second, and it says east. And it says the magnetic field is going into the page. So this drawing here is actually not right. So we're going to ignore that drawing. Alright, so let's see, what do we have here? So we want to figure out the force on this. F equals Q, which is 1.6 times 10 to the negative 19th coulombs, times the velocity, 3 times 10 to the 7th meters per second. Oh, and I forgot to write the magnetic field. That was the last part given to us in the problem. Just right here. B is equal to 4 Teslas times 4 Teslas. And now again, we're going to plug this in our calculator. So clear 1.6 E19 negative times 3 times 10 to the 7th times 4 gives us 1.92 times 10 to the negative 11th. And that's it. Oh, and the last part is to identify the direction. So to get the direction, we're going to use the right-hand rule. So this picture isn't very helpful, but we know that the velocity is going east, which means on my paper, we're just going to say that that means going to the right. So my index finger points to the right. The magnetic field, they say, is going into the page here. So index finger goes to the right, middle finger points down. My thumb then is now in the up direction. And so up means north. So now that means that the force is up or north. Okay. Let's take a look at this next one. Dean is hunting Northwest Territories, where the Earth's magnetic field is 7 times 10 to the negative 5 Teslas. He shoots by mistake a duck decoy, and the rubber bullet he is using has a charge of 2 times 10 to the negative 12th coulombs as it leaves his gun at 300 meters per second east. What is the magnitude and direction of the magnetic force? This is actually the exact same problem, but let's do this one as well. So it tells us that the magnetic field B is equal to 7 times 10 to negative 5 Teslas. It tells us that the charge that the bullet acquires, Q, is equal to 2 times 10 to the negative 12 coulombs. And the velocity is 300 meters per second east. So the first part is easy. The magnitude, say F, the magnitude is equal to qvB, which is equal to 2 times 10 to the negative 12th coulombs, times the velocity, 300 meters per second, times B, which is 7 times 10 to the negative 5 Teslas. And here, 2 times 10 to the negative 12th times 300 times 7 times 10 to the negative 5th gives us 4.2 times 10 to the negative 14th. And now we have to figure out the direction of this. So the magnetic field is north, which means up, and the charge is moving east, which is to the right. So index finger points to the east. My middle finger points north or up, and then my thumb is now pointing out of the page. So this comes out of page. Alright, so trying to think what other problems that you might encounter. The last one that you need to know is there's one additional version of this equation. qvB is one version. The other one is IlB. And this one's used in, let's look at problem number 7 right here. So in problem number 7, it doesn't give us the charge, but does give us the current. So this is I, and it gives us the length of the wire. This is L, and here we have the magnetic field, B. And so the other form of the equation is the force is equal to I times L times B. And so here we have those three parts. And so we take the current, which is 8 amps, multiply it by the length, 0.5 meters, multiplied by the magnetic field, 0.70 teslas. 8 times 0.5 is 4. 4 times 0.7 is going to be 2.8. Let's just double check to make sure that's right. So 8 times 0.5 times 0.7, 2.8. And the force is 2.8 newtons. Alright, so there's a couple other problems that are assigned. I'm going to post both the handout here on Classroom. If you don't have a printer or unable to print this, just do it on a separate sheet of paper. When you're done with it, please take a picture of it and upload it to Classroom. If you have questions or problems with doing these, reach out by email. I'm going to be online every day from about 7:30 to 3. So anyway, I hope you guys are all being safe and staying indoors and spending a lot of good time with your family. So I hope you're all safe and healthy. I will talk to you guys soon. Take care. Bye-bye.